Okay, so yesterday we started into the second main chapter, which was on dynamics. We're going to start studying forces of pushes and pulls. Towards the end of the lesson, we started seeing the advantage of drawing what's called a free body diagram. If I imagine all my mass is squeezed into a singular point, a free body diagram will label all the tug of war, all the pushes and pulls that apply on your object. And that's usually our starting place to these problems. So let me just start off with a quick warm-up question here. Really easy. If it feels too easy, it's okay, right? It's not meant to be very hard. Let's imagine here's a wall and I have a ceiling. We have an object that's being sort of strung by two strings. One string is sort of at an angle, the other string is holding this way. Again, I tell you this problem here is static, which means this thing here is at rest. That means when I run the clock, there's enough tension along the strings to actually support this mass here. See if you can draw a free body diagram. So draw a free body diagram. And usually we shorthand a free body diagram as FBD. Again, even if they don't ask you for it, this would be a good starting place. So try doing that free body diagram for this picture and as well for another picture here. Let's say I have a sort of a cart. I'm dragging a cart behind me here. I'm applying a force here along an angle. I'm trying to just sort of pull it to the right. And let's imagine that this cart moves to the right. And again, we're going to come back in a later lesson to actually analyze this in more detail. For the time being, I just want you to do a free body diagram. All right? So, what are the forces that act on this? Well, this first object here is just hanging in midair. Let's squeeze into center mass. There's always going to be gravity, right? Gravity always wants to pull things towards the ground. What's keeping it from falling there? This time it's not a normal force because this thing here is actually not sitting physically on a surface. What's actually supporting it are the strings. So case in point here, if I cut this string, suddenly this mass here is going to start swinging downwards. So this string here has to be applying a force. It's actually applying a force sort of along the string. I'm just going to call that a tension force. So this is a tension force from the string. And in a similar fashion, what if I cut this string, then it's going to start rocking back and forth. This one here also applies a tension force. That also is another tug of war that's trying to support the thing so it can stay at rest. The cart problem is a little more interesting here. So the cart is just sitting there. Again, gravity doesn't care. Gravity just pulls straight downwards. You are definitely applying force here. I'm trying to drag it along. I'm holding along the handle. I'm trying to pull it at this diagonal here. But what are the other forces that actually act on it? Probably when I pull this cart here, I'm imagining the cart is fairly heavy. I'm like that bird analogy from yesterday. I'm probably not pulling hard enough to actually lift the thing off the ground. I'm not getting this whole thing to slide. I'm getting this thing here just to slide along the surface. So what's happening here is there probably, because I am on a surface, there's probably a little bit of force due to a normal force. From the surface, it needs to make up that difference is to make sure that this cart here doesn't suddenly fall through the ground. What other forces act on it? We will see some vector stuff come back a little bit later on. As I apply a force that's sort of up and to the right, I can break that up into the x part and the y part. Those are just components of this red arrow here. Those aren't individual forces there. But seeing as I'm going to drag this one here to the right, as long as the ground is sort of rough and there's sort of jaggedy edges and surfaces here, we would imagine there's actually a friction force that actually goes against you. There's actually an FF that's always fighting motion. If you just practice for normal force here, just for review from yesterday here. In this case here, if you looked at the size of the normal force, if I ask you to fill in the blank here, would the normal force be, is it bigger than, is it equal to gravity, or is it less than gravity here? What would you say? In this case here, let's imagine I wasn't doing anything. Let's imagine I didn't actually drag it. So if I don't apply any force, in that situation, Fg should equal to Fn. You'll notice because I apply a force up and to the right, I'm actually supplying force upwards. This is like that bird problem from earlier. I'm not pulling hard enough to actually lift the cart off the ground, but I am helping it a little bit. So therefore, normal force is sweet. I can pull a little bit less. The normal force should actually be less than gravity. In fact, case in point here, you should be Fn plus whatever I'm supporting it should counteract gravity just to make sure we don't fall through the ground. And therefore, the Fn is actually smaller than gravity. Again, more on that later on. For today, what I want to do here is I want to summarize for you something called Newton's 3 laws. Again, in honor of Newton here, he did a lot of work with this dynamics here. He basically summarized for us our understanding for forces, and that's a good place to start off. So let's do Newton's 3 laws. Let's start off here with Newton's first law. Newton's first law says an object remains at constant velocity. An object remains at constant velocity unless a net external force is applied. Yeah, you're going to find sometimes the wording is a little bit different, but again, what's the implication here? So what this is saying here is an object remains at constant velocity. Sometimes you can call that uniform motion. But be really careful, constant velocity doesn't necessarily have to mean rest. If an object is sitting there, if the velocity is 0, and it's supposed to be constant, if I'm supposed to stay there, sure, it's going to then remain at rest, no problem. But what if we were in space, right, sort of away from any planets, right, sort of no real external forces acting? What if I give this object here a quick push, and let's say this velocity here currently is 10 meters per second. As long as I don't push on it anymore, right, I'm not constantly my hand behind it and constantly pushing it forwards, this object here is just going to constantly stay at 10, constantly stay at 10. That also obeys this law here. We are remaining at constant velocity because there are no sort of net forces that are acting on it. So just because we're constant velocity, be careful. It doesn't always have to mean rest. It just means that your speed is constant. Your speed can't change. So what this is implying to you is force is not needed for motion. You can move, no problem. But the type of motion that you're limited to is you're limited to uniform motion. You're limited to staying the same speed. Right? So as long as basically this law can be thought of, well, as long as you're not doing anything to the object just continues doing what it's doing. If it was at rest, it's going to stay at rest. If it was slowly sliding along, it can be moving at 10, no problem. It's just going to keep moving at 10 until you do something to it. What can you do to it to kind of push it out of this law here? You have to be external to the system. You can't be sort of, let's say this is a book here, the book can't push on itself or anything like that. If you were outside the system, you can act on this book, right? You can lift this book, you are external to the system. If you supply some net force, you can get it to change what it's doing. Imagine this were you're swimming in a swimming pool here. You can lift your shoulders up all you want because you're part of the same system. You're internal. You can't actually save yourself if you accidentally are getting tired and at risk of drowning. You'll need a lifeguard to come up behind you. The lifeguard is actually external to you. When he applies a force, that force can actually pull you up out of the water. So that's what we mean by this external part. There's also one other implication here. What is the net force? Net force is sort of like after you factor in the tug of war, after you cancel out the forces that will cancel, do you have any overall force remaining? Do you have a force that is overall unbalanced? In junior science classes, you may have called it an unbalanced force. So the way that is, let's imagine this second scenario. This book here is just going to continue forever at 10 meters per second. Let's imagine I'm standing behind it, and let's imagine I actually push 5 newtons, right? If I were the only person pushing, I don't obey the first law anymore. I'm now going to be able to change the velocity. However, if I have a friend that's actually standing on the other side, also pushing 5 newtons, I can put one as positive, one as negative, just to indicate direction, or you can just see that from the picture here. In this case here, there is no net force. I'm trying to push a 5. It's going against me 5 as well. These forces cancel out. Overall, my net force is 0. Overall, it's as if nobody is pushing on it, right? We're both canceling each other out. And in that case, this object just continues doing what it's doing. It's going to continue moving at the same speed. We're going to sort of qualify that a little bit here in Newton's second law. Newton's second law says for us here, if there is a net force, if it was just me pushing and no one was going against you and there was some uneven tug of war, some unbalanced force, net forces cause objects to accelerate. So you didn't need a force for motion necessarily. You can be moving, you can be sliding along, but you're limited to sliding on at the same speed. What a net force does here is it actually causes an acceleration. By doing a push and pull that's not canceled out, I'm actually causing things to speed up or slow down. So net force here in words is actually a little bit harder. I'll give you the formula in just a second here. Net force is actually proportional to mass and acceleration. So if we are outside the system, if we're external, if there is a net force, if there is an unbalanced tug of war, it's going to cause the object to change from doing what it's doing. So what's going to happen here is, this case, again, the math of it is a lot easier. This is on your formula sheet. We have F net. I introduced that little sigma notation again. We saw that a little bit with vector addition here. Sigma just means add up. As you factor in all the tug of wars in the picture, the net force is actually proportional through mass and proportional through acceleration. So simply it's just m times a. Let's do a few different scenarios of this here. Let's pretend you apply the same force. All right? So in this system here, I have a small mass and I have a big mass. And it was told out to me how hard I push. I'm going to push both of these with the same force. Now, I am the only force, so this is going to be a net force. No one is canceling me out. So this object, maybe it started from rest. Because I have a force, it's going to cause an acceleration. But what we can see from this formula here, when I have a tinier mass, if I use that same force, I'm going to have a relatively bigger acceleration. So again, we had said yesterday, lighter masses are easier to accelerate. They're easier to speed up. This one here will change speed a lot quicker. Whereas if I have a heavier mass here, this one, I'm pushing at the same sort of force, the same amount of newtons, but it's not really accelerating. It's a little bit slow. It's sort of dragging its feet a little bit here. It's a little bit harder to accelerate. So that's one way of seeing this formula. Another way of seeing this formula here is, what if I apply different forces to the same mass? So what if I sort of scratch that picture? I don't have sort of one small mass, one big mass. Let's just have sort of one medium mass. And what if I decide this time to actually push at different strengths? So the first time I'm sort of pushing with a really, really tiny force here. The second time here I'm going to push with a gigantic amount of force. Well, if I have the same amount of mass, if I have a tiny force, that's going to amount to a tiny acceleration. So in this case here, we can even just qualify for the other one here. Tiny force, not as big acceleration. The larger the force, bigger force means bigger acceleration. So again, we didn't need force for motion. Motion was fine even with no net force. But if I do apply net force and it's not cancelled out, it'll actually cause the object to actually speed up. And again, we see that in the formula. This time, if the mass is constant, the larger the force, the bigger the acceleration is going to be. It's sort of like saying, well, you push harder, you expect it to start speeding up faster. That's fine. One more interesting case here is we can do the example, what if we were the same acceleration? Right? Now, how could we do that experiment? Well, it's actually not that hard, right? We did this back in our kinematics. Let's take a small object, maybe a tennis ball. Let's take a big object like a textbook. Both of these are being accelerated due to gravity. What's the acceleration from gravity? Well, acceleration is equal to negative 9.8. It's in the downward direction. So both of these objects, whether it's a light object or a heavy object, both of these objects are actually going to hit the ground at exactly the same time. We had done this with our projectile motion. We had sort of said, well, the y part doesn't actually care about the x part. You can do this experiment for yourself. It doesn't matter the mass of the object. Because gravity accelerates everything at 9.8, the objects will actually hit at the same time. However, there is something different about them, right? Not just sort of the speed at which, how long until it hits the bottom. I would be much more worried about a textbook falling on me than a tennis ball falling on me. Well, why is that? Well, again, if F net is equal to ma, this time acceleration is constant. This time a is always going to be 9.8. What's going to happen, because force net and mass are proportional, as the mass increases, the net force from the textbook will push more of a oomph. There's more of a hit when this mass here is large. So you can make a note here. Although they do hit at the same time, the heavier mass or the larger mass, the heavier mass will supply more force. There's going to be more of a push from that heavier mass there. So that's nice. So far we have Newton's two laws here. Newton's first law said, if there is no net force, objects just continue doing what they're doing. Newton's second law then says, all right, if there is a net force, if there is an unbalanced force, work out your tug of war, work out how much is left over. That net force is now proportional to mass and acceleration. Tiny objects accelerate faster. If I apply more force, more acceleration, more mass, also more force. Right? So all those things are proportional to each other. One thing I just want to qualify in this statement here, net force by itself, this is not actually a force. Now you're going to say to me, well, why did I bother learning this if this is not a force? When I say it's not actually a force, I'm not saying it's a net force that actually does m times a. This is actually only what's left over from the tug of war. The tug of war is actually where you actually have forces. So for example, in this case here, who's applying this force? Maybe it's me that's applying force. Maybe I'm doing an FA. Maybe there's a friction force against me, FF. The actual tug of war is my FA, how hard are you pushing, and the FF, which is the friction force which is trying to slow you down. That's the actual tug of war. In that situation, maybe I have an FA that's larger than FF. When I do F net, I'm basically saying what's left over. What's FA minus FF, right? The actual pushes and pulls was me applying a force, applied force, and the actual pushing and pulling was the friction. The net force is just the numerical value. It's just how much didn't cancel out. How much is actually unbalanced. You can't say, oh, it's a net force that pushed this thing. The net force itself is not a force. It's just what's left over. It's just what's remaining from the actual tug of war. That's why a free body diagram will be really helpful. The free body diagram actually tells you which ones actually are forces. We're going to do this picture of net force. We're going to do this. Well, you pull this way and you pull this way. How much doesn't cancel out? In this case here, we can then calculate net force. Once I know a net force, I can do m times a. So do take that note down. The net force here itself is not a force. We had said forces aren't needed for motion. You can sort of reword Newton's second law here. Forces cause acceleration. Forces cause you to actually change speed. It could be a speeding up. It can be a slowing down. But it sort of changes you from what you were doing from before. You're not just going to continue on. If you're at rest, just sitting at rest, or if you were moving, you're going to be speeding up or slowing down. Forces are needed for acceleration. Just for completeness sake here, before we do another question, let's switch over to Newton's third law. Newton's third law says forces exist in equal and opposite pairs. In elementary school here, you may have talked about, well, forces are action-reaction forces. That's sort of talking about this law here. So let's imagine you get really frustrated with physics one day. Here you are, right? You have a wall. And what I'm going to do here is I'm going to run against the wall. I'm going to apply a force of 10 newtons. Just to put a sort of feel of this here, 1 Newton would be sort of how hard you need to lift a regular size apple. So I'm sort of pushing fairly hard against this wall. I'm assuming, even though I'm running really hard against the wall here, I'm assuming the wall is really sturdy built, that I don't actually run through the wall. For the wall to actually stop you, the wall actually supplies a force that's equal. It's going to supply 10 newtons, but it's also going to be in the opposite direction. It's going to be in the negative direction, or you can see that in the picture. I'm going to push to the left as you're going to drag to the right. Now you get really frustrated and you run against the wall even harder, and you now say, okay, I'm going to now run at it. I'm going to supply 100 newtons, right? The wall still has to supply an equal and opposite force here. It's going to go against you 100 newtons. It's equal in size, just enough to counteract your force, just enough for the wall to hold itself together. If the wall actually broke down, that means there was some limit to how hard the wall would actually push. Maybe it's trying to supply 100, but if it can only supply 80, well, yeah, you win out then. Then you would have a net force. Then you would keep going through the wall there. Right? Normally it doesn't happen there. So that's what Newton's third law says here. Forces are equal and opposite. We already saw the example with between the Earth and the Moon. Right? So yesterday we had the Earth and we had the Moon. Even though we have the Earth as a much, much larger mass, because forces are equal and opposite, however hard the gravity is pulling the Moon towards the Earth, that's going to actually be equal and opposite to the Moon pulling the Earth. However, we just did Newton's second law here. Because the Earth is so much more massive than the Moon here, the Earth is way bigger. So the acceleration is small. So how come we only see the Moon is in orbit, the Moon revolves around the Earth, and not the Earth around the Moon? It's because the Earth is so much larger, right? A smaller mass is much easier to accelerate. Now, I do want you to be careful with this law here. Sometimes people just focus on this opposite part too much, and they start getting confused. Let's imagine back to my earlier question. Let's say I just have an object just sitting there, right? It's just, let's say it's a 50 kilogram object. I can start off with a Freebody diagram. We did these numbers yesterday. We always start off calculating FG, calculating the weight of the object. So 50 times 9.8, well, that gave me my 490 from yesterday. The force of gravity acting on this is 490. I do want to say 490 down, but my Freebody diagram already shows me that it's in the downward direction. I don't need to write that in words. But I know that, well, there is a normal force, right? I know the surface supports me. I know the surface is actually pushing 490 going upwards. When I say equal and opposite, I'm not saying necessarily that the normal force has to always be equal and opposite gravity. When I say equal and opposite pairs, I'm actually talking about each force individually. So if I actually wrote this on words for you, for example, this FG, this 490 is how hard the Earth pulls on the box. When I say equal and opposite, I'm saying that FG in itself already has an equal and opposite pair. The box here is actually pulling the entirety of the Earth. The equal and opposite part is actually the box pulls on the Earth exactly the same 490. Now again, how come we don't see the whole Earth whoosh towards me? Because the Earth is much more massive, right? In the same way here, my normal force, what's the normal force? The normal force is the ground pushes up 490 to support you. But because this is also an equal and opposite pair here, in this case here, I'm also saying here, as your box here is just sitting there, the box pushes the ground 490. So just be really careful. Yes, I know in some cases, especially when we deal with normal force, oh yeah, normal force has to support against gravity. It has to make sure it cancels out the forces. That's all still true. But especially when we deal with Newton's third law, when we say equal and opposite pairs, we're saying every single arrow itself, there's an equal and opposite pair for force of gravity. There's a separate equal and opposite pair for the normal force. Right? So just watch out for that. You can see that a little bit better when the two objects are really far away. Just like the Earth pulls on the moon pulls on the Earth. Right? So let's just utilize some of these laws here. We're going to have a quick look at a spring problem. So looking at springs. Right. In fact, a lot of our weight scales, we call them Newton scales here. A Newton scale would typically have mass readings on one side and newtons on the other side. We know from the formula it's really easy, right? Fg is equal to m times g. Basically, there's a little hook on the bottom of the spring scale here. You can weigh down the object. There's a little slinky inside the string here. As the object itself gets heavier and heavier, let's say that's a light object, let's say it's a heavier object, it's not like the whole bar, the whole meter actually changes, but what actually changes is the slinky inside gets more stretched out, the slinky gets pulled harder, and basically what's happening here is we're figuring out how far is the slinky being pulled to counteract this one here. That's actually going to make the mark a little bit lower, and therefore you can read a higher mass and also a higher amount of newtons as well. So we'll use springs or slinkies. In this case here, we're going to actually talk about them in terms of Hooke's law. Hooke's law applies to springs. And again, usually describing in words here is actually more confusing than actually with formulas, but I'm going to do it anyways here. The force along a spring, the force is proportional. Force is proportional to the spring displacement. So what I want to show you here is, at first, even when you had no object, the slinky is already of a certain length. Let's call that L naught, right? That was the original length that we actually had. That's not the length I'm talking about. I'm talking about when you now weigh down that mass there, when this slinky here is now stretched beyond what it wants to be, now maybe the full length here is just L. When I do the formula here for Hooke's law, usually we say Fs. This is the spring force. Because it is actually a force here, it's measured in newtons. It's proportional, so there's going to be a constant here. It's going to be proportional through K, but it's going to be proportional through the displacement, just the change in the spring's length. And in this case here for my picture, the delta x is going to be given by L minus L naught. So if you just want to match up in the picture here, I already knew the slinky already had some L naught. That's not the force that's being applied. My displacement is, now that I pulled it this much extra distance, it's this extra distance that I'm calling x, And in this case here, you can calculate it mathematically. L is the entire length. If I subtract off the L naught, that gives me the extra little bit that the slinky is being pulled. So on your formula sheet here, we do have the spring force is proportional through kx. Let me just write down some of these words here. This is going to be the displacement. I want to note down here, this is the extra length that we stretch it out. So it's pulled farther than it wants to be. It could also be I push the slinky tighter than it wants to be. It always is going to go against me. It's going to try to restore its original length. So extra length, it's stretched out, or the extra length that is actually compressed. Both are fine. And I'm going to give a special name to this proportionality constant here. The proportionality constant here, we can just call this the spring constant. It's a constant that describes my slinky. We can just use dimensional analysis to figure out what units these should be. Because I'm going to be multiplying a meter and then ending up with the newtons, I better have a newtons above and a meters on the bottom, and therefore my meter cancels the displacement of meters and it picks up the newtons for the slinky. It's this spring constant here that actually depends on the material. Some materials are just easier, more stretchable than other materials, and basically this number describes how easy it is to stretch. The bigger this number, the more rigid, the more tighter the string, you need to supply even more force to cause it to stretch by that meter, stretch by that displacement. So let's just do a quick question here. Also sometimes, right before we do that, sometimes they actually give you the formula with a negative kx. I usually am okay with just being f is e to kx because this negative part just stands for its opposite directions. You stretch it out farther than it wants to be, the slinky wants to pull it tighter. You squeeze it in tighter than it wants to be, the fs is going to go against you. It's always opposing you, but the value, the size of it is always k times x. So let's just try a quick question here. Let's imagine I have a slinky. It's hooked on to the side here. At first, this is my slinky. My slinky is currently 5 centimeters long. We have a 10 kilogram object and we're currently at rest. Right? So everything is cancelled out. We'll ignore gravity for the time being. What I'm going to do is I'm going to start applying a force. So by applying a force here, I end up pulling the slinky. It's sort of unwinding itself. It's stretching way farther than it wants to be. I have the same mass, the same 10 kilograms. It also is at rest because I'm supporting it. And what I'm going to do here is I'm just going to tell you how hard am I pulling on it. Let's say I'm pulling on it. I have to apply a force of 20 newtons for this to happen. Right? So we started off here, the natural length. Right? So this was the original length of the slinky was 5 centimeters. It's now going to stretch out here. I'm going to give you the total length from the wall. Let's say the total length is actually 12 centimeters. Right? So this is fine. The FA is pulling outwards. When we do Hooke's law is opposite it. That's why we have that negative symbol. Hooke's law gives you your Fs here. And the Fs is going to be negative k times delta x. As you pull out a slinky farther and farther than it wants to go, the slinky is going to resist you even more. It's going to pull harder to try to restore back its own length. So I already pointed the arrow in the negative direction, so I've taken care of that part. What we're interested in calculating, the only unknown is actually the spring constant. How tight or how rigid is my slinky here? So we're going to do this. If I pull out with FA 20 newtons, because it's at rest, I know my slinky is also supplying 20 newtons. Why do they have to be equal? Not because of Newton's third law. Equal and opposite pairs would apply to FA and FS separately, but they have to counteract each other so that if the FA were bigger, the slinky would keep stretching out. If the FA were tinier, the slinky itself would start contracting, but because it's at rest, we know they're actually equal. So 20 has to equal to k. My x has to be the extra length that's displaced. It's neither the 5 nor the 12. It's actually the difference here. We're stretched 7 centimeters further than I want to be. I'm just going to convert this to meters, so 0.07 meters. And then just by dividing those two there, 20 newtons divided by 0.07 gives me a constant roughly 286, and we already said the units are going to be newtons per meter. And that is now a constant for my slinky. So if later on you decide to pull it out 8 centimeters or 10 centimeters or with 500 newtons, whatever, this constant it now stays true for the material. This part here depends on the material. So maybe in the metal or the plastic that I make the slinky here, this tells me for every meter that you want to pull the slinky, notice that in this context here, I'm not pulling it a full meter. I'm pulling it a fraction of a meter. But if I just sort of scale it up, it would take a total of 286 to pull it up by meter. If you double that, you pull it up by 2 meters. It's a nice linear correlation. In fact, we can do this graphically here. If I plot for you the force that I steadily increase, and I actually plot this change in displacement, I plot how much extra distance the slinky is actually being pulled. This one here, the spring constant will actually give me the slope of this graph here. Because it's telling me, let's say I want to pull it out 1 meter, it says, oh, that means you need to pull it out 286 newtons. If I want to pull it out 2 meters, oh, it's going to be double that here. 2 times 286 here is equal to 572, right? And basically, Hooke's law, graphically speaking, K is actually the slope. So sometimes I ask this question here. It's the slope of this force delta x graph. And this is the first time we're seeing this F delta x graph, right? We saw displacement time, velocity time, but depending on your variables here, what would I get if I took the rise, right? This is the force, and divided by the delta x. That's just a slight sort of rearrangement of this one here. Well, K is equal to the amount of force divided by the delta x. So K is the slope. One important note here is Hooke's law is nice, right? It's a nice simple formula there. Hooke's law actually only applies, there's a limit to it. This applies to small forces. Because any of you that have had a slinky or a spring before here, you can find, well, if I pull it way farther than it wants to be, it just starts getting unwound, and it's like I'm pulling it really hard and it's not being able to come back. It's now permanently deformed, right? And that's sort of showing you here, well, it isn't linear forever. It's linear up to a limit. So as long as you pull it within the sort of natural stretchiness, the stretchy lengths, and you don't actually deform it, it should apply. So Hooke's law only applies to small forces, and we'll just say this is before deforming. And slinkies are notorious for somehow, no matter how nicely you put them away, they just over time, they just steadily unwind, and that's sort of an indication Hooke's law doesn't apply anymore. I want to end up with one more question here. This one here will just get you to think a little bit here. Let's imagine we have, here's the roof. I'm going to have a slinky, right, or a spring. We have a 500 kilogram object. And what I'm actually going to give you is I'm actually going to give you the acceleration. So I actually know this slinky here is constantly, it's going to pull it upwards. The acceleration is going to be 3 meters per second squared. This thing here is actually going to be pulled upwards. So I have a 500 there. What I want to do in this question, I want you to start off, draw a free body diagram. Draw a diagram with the center mass with all the arrows labeled which are your pushes and pulls. I want you to calculate, I'm going to word it very carefully here, the magnitude of the net force. I'm going to rehash that whole notion. Net force itself is not a force. We'll see that in this picture. And then C, I want you to find what is the Fs and the delta x. How hard is the slinky actually pulling? And the displacement, how much further is the spring stretched beyond what it wants to be, given the K value here. Let's make the K value, 1,300 newtons per meter. So difference, slinky here, this K here is much larger than the other one, so much more tight, rigid, but let's just go from there. As always, I want to start off with a free body diagram. What forces act on this object? So I'm going to imagine all 500 kilograms is squeezed into a tiny mass. Well, we always know there's gravity, right? The only reason why it's hanging here, right, is because gravity is pulling downwards on it. The nice thing about gravity is you always have a formula for it. Fg is equal to mg. So since you have the mass, you can simply go 500 times 9.8. How hard is gravity pulling on it? It's an action at a distance force. It doesn't physically need to be on the ground. It's pulling on it 4,900 newtons. That's just gravity, right? What other forces act on this object? Is there a normal force? Well, this time there is no normal force because the ground may be somewhere down here. I need to be in contact, actually touching, for a normal force. But what is actually supporting you? Earlier we had just called it a string, so it's a tension. This time it's actually my slinky that's actually supporting you. This time I actually have an Fs that's going in the opposite direction. Again, not equal and opposite. Each of these arrows have their own equal and opposite pair. But I'm just looking generically here, what are the forces that act on this diagram? Fs, again, we actually need to calculate what that is in this question here. Fs has to pull what it needs to so that we actually accelerate upwards at 3 meters per second. So let's just think through the options here. Let's say the Fs is exactly the same as gravity. Gravity pulls down 4,900. If Fs is also 4,900, the net force is 0. Newton's first law says if the net force is 0, we're just going to continue doing what we're doing. In this case, it's actually 0. But in this question here, we're actually told it actually does accelerate. For me to accelerate, I actually need to make the Fs actually larger than gravity. It needs to be big enough to counteract gravity. It can't let this object fall, but it needs to make up this difference, pull hard enough that it actually causes this upwards acceleration. So in this case here, I'm already assuming the Fs has to be bigger than gravity. So let's just try it out here. That's actually my free body diagram. It's just an Fs. The arrow has to be larger. There's an Fg. Those are the only two forces that I have. We can do part B. Well, Newton's second law gives us the magnitude of net force. F net is supposed to be m times a. So if you want to have a mass that's 500 kilograms, and if you want to accelerate upwards at 3, you need to have a wind of 1500 newtons. Again, you cannot say to me, well, what is actually supplying this net force here? Oh, it's my net force that pulls upwards 1500. Net force is not a force. What's the actual tug of war in this case here? The actual tug of war for my picture is actually, it's my slinky that's trying to pull it one way, and it's gravity that's trying to keep it on the ground. What net force is basically, this is how much is unbalanced, how much is unbalanced left over from the tug of war. So earlier we had said Fg is supposed to be 4,900. If I look at the tug of war, usually I just go bigger minus smaller because I know I have to win. I know I have to have a net force that goes upwards. My unbalanced force has to have a net upwards win. So therefore I can say F net is given by my tug of war. My tug of war this time is Fs and Fg. It's Fs minus Fg, bigger minus smaller. And this one here has to give me a win of 1500. Again, let me just put some numbers to this here. So Fs, I don't currently know what the value is. I don't know how hard the slinky is pulling. The Fg, you actually had 4,900. If the Fs was just 4,900, 4,900 minus 4,900 is 0, there's no acceleration. But because I have to have a win of 1500 upwards, how hard does the Fs have to be? Well, Fs actually has to be 4,900 plus 1500. You add those two together here. If the Fs is 6,400, it's going to use 4,900 just to counteract gravity, just to make sure this object can stay free floating. But it needs to also supply not only 4,900, but an extra 1,500 to allow a 500 kilogram object to actually accelerate at 3. So what I want to show you here is Newton's second law is great, but it only gives you the size. It only gives you the unbalanced amount has to be 1,500. You'll notice I actually had to add that 1,500. The Fs has to not only counteract gravity, but also needs to supply the net force to give you 6,400. You're not going to get this formula anywhere in your formula sheet because it really depends on the scenario. It depends on that exact tug of war. Once you've done that here, the problem is fairly easy. Because I have Hooke's law here, Fs is supposed to be Kx. I'm not going to worry about the negative or the delta because I remember it's permanent. So it's going to be 6,400. Fs in total, the slinky has to pull 6,400. The K value they gave me was 1,300. How far is this slinky here stretched beyond what it wants to be? I just do a quick division there. This is going to be in meters. So 6,400 times divided by 1,300 gives me an x of 4.9 meters. Right. So again, let's just backtrack here. What have we just found? We saw from the Freebody diagram the tug of war this time is Fs against gravity. We saw that because this object here is known to accelerate upwards, the Fs actually has to be bigger than gravity. To calculate how much bigger it has to be, we calculate the net force. That's what Newton's second law gives you. F net is equal to ma. I have to have a wind of 1500. If gravity I know is pulling you down 4,900, Fs winning by 1500 pulls 4,900 and 1500, so it supplies 6,900. Fs is constantly trying to, right now the slinky is stretched out farther than it wants to be, right? Fs is actually, like, from compared to the natural length here, Fs is actually 4.9 meters further than it wants to be so that it can supply the 6,400, so that it can supply this acceleration of 3 meters per second squared upwards. We're going to pick it up from there tomorrow, practice through some questions, and we'll see how you do. Thanks, guys.